σας δώσουμε μια ομιλία πάνω στην εμπειρία μας στην μαγνητική τομογραφία. Είναι χαρά μου που είμαι στο συνέδριο, γιατί το διδακτορικό μου ήταν στην βιοϊατρική μηχανική, οπότε και εγώ είμαι μέλος του κλάδου. Πιο πολύ δουλεύω με τα mechanical groups, παρά με τα μηχανικά, αλλά τώρα τελευταία έχουμε αρχίσει να δουλεύουμε και στην Ευρώπη. Επειδή όμως δουλεύω 26 χρόνια και όλα τα όντα στα αγγλικά, θα κάνω την ομιλία μου στα αγγλικά, αν βλέπετε. Okay, so my talk is going to be about textual analysis for multimodality magnetic resonance imaging. In particular, I'm going to talk about pediatric tumors and how we apply this approach to this problem. Now, about 15 years ago, my motivation was to start working in this area, in particular look at the advancement of imaging techniques, but also the advancement processing of images that come from various modalities that relate to magnetic resonance in the clinic. And my motivation was because if you look at the target tumors, if you look at childhood tumors across the UK, the brain tumors, although it is a very rare disease, we don't have, thankfully, too many cases every year. You can see that from the samples we have. It is still a painful disease for children. So about 18% of these tumors appear in the brain, about 7 to 10% in the rest of the central nervous system. And it's the most commonest cause of death in this area. And despite that we have done a lot of progress in our improvement of survivability of these children, we have 33% of children dying more since 2007 by this terrible disease. Now, why magnetic resonance imaging? It is very useful because from the point of view of clinicians, especially radiologists and neuro-oncologists, MRI is very good in giving us some information about the anatomy and the structure of the tumor at the level of diagnosis. That's an example of a posterior fossa tumor, terrible astrocytoma. After we do the surgical resection, MRI is very important to see the progress of the disease and also the healing of the disease. And of course, usually with children, we try to do chemotherapy to improve and reach the optimum position for them so that we can improve the survivability for them. But the difficulty radiologists have is to discriminate visually these tumors. And this is where I built all my thesis for this discussion today. So these are two tumors, again in the posterior fossa. We have three major types of brain tumors in this area. Unless you know some clinical information, it is very difficult to discriminate between the two types. So if you see at these images, the tumor structure looks almost similar, slightly offset, because it's of two different patients, and it's very difficult to decide if this is an ependymoma, an ependymoma, or an astrocytic tumor. And actually, of course, I know the answer. So here we have an ependymoma and ependymoma. This is a more rare tumor, more aggressive. This is more well-known tumor. It is becoming now a tumor that is described by four different genetic types. So maybe it is 4 different diseases. So that's the difficulty. And because of that difficulty, although the initial characterization of these tumors has to be part of the radiologist's job, different brain tumor types do not show these differences in physical appearance. So using conventional MRI is always difficult to do that discrimination. And actually, if we want to do accurate diagnosis, we can also do it at the first point. And what do we have to do is to do biopsies. Now, that's okay in adults, not all adults, but in children, in particular in the area where most of the tumors reside in children, in the back of the brain, it is almost very difficult to do biopsies. A biopsy would kill a child at an early stage. So we need to find ways of doing quickly an initial diagnosis, maybe in a quantitative, maybe accurate and non-invasive way. So the thesis I'm putting is, can we use texture information from images to do that? In addition to that, maybe we need multiple imaging modalities, and as much as possible less radiation from children. So I'm going to put the concept of functional imaging in the context of magnetic resonance modalities as part of that exercise. So here we are. This is the challenge we have, and this has been the challenge I have been working with my team and the team at Birmingham University and the Children's Hospital, together with another 7 hospitals across the UK, to try to resolve this in different ways. Now, let me explain what do we mean by functional imaging. It's not what people sometimes ask me, well, you do the field psychologists do functional MRI. No, it's not that. Actually, it is a set of methods that allow us to understand better the tissue properties. Things like cellularity or ultrastructure, metabolism, vascularity. So we call these techniques functional imaging techniques, although they're not fMRI techniques, and I'll talk to you about this in a minute. And they help us a lot. We have evidence, and I'll show you the evidence in terms of texture analysis that help us a lot in the diagnosis, prognosis, treatment planning, and monitoring of the disease, especially in children. So, as part of the CRUK, Cancer Research UK 10-year program grant, we have been looking at using these functional imaging techniques in order to investigate children's cancer in the brain. And this constitutes from an array of things that tell us about metabolism, so magnetic resonance spectroscopy. It's not very clear, but you can see some interesting spectra that tell us a little bit about the biochemistry of the brain. Quantitative imaging based on parameters of MR, structural MR, like T1 and T2 measurements. Looking at the properties of water diffusion, so that we understand particular cellularity issues, together with perfusion, which we look at vascularity, and then combine structural and biochemical information to maps that tell us about the metabolism of the tumor, or even we can create, through diffusion, 3-dimensional representations of the tracts of the nervous system. Actually, this is my brain. And if you look at this very carefully, it misses half of the brain tracts. This is a joke my physician is always saying it's always a vessel we don't have any brains, and we can prove it scientifically. So there you go. So how do I to show that? I will talk about my physician that I have to information. So let's talk a little bit about these functional imaging techniques before I come to the point of how texture can be combined with these. So, in addition to the conventional MRI in the clinic, by using the same scanners, the same coils, now we can, on the basis of an image, place a voxel in the anatomy where the tumor is, and then in that region of interest, we can acquire metabolic spectrum. It's like we do biochemistry. And NMR has preceded the clinical work, so it's like we bring the old chemical NMR into clinic. And of course, with offline processing, we have developed a particular tool that allows us to accurately quantify metabolites. We can find different metabolites, the quantities and what they mean. And actually, in terms of tumors, we have shown and we have published various publications in the advanced review at Oncology. We have been able to say something about these metabolites. So there are some good ones and some bad ones. So for example, inositol metabolite is usually linked to meiosis, and actually it's very, very important for growth of tumors and oncogenesis. Total choline also tells us about the cell turnover, and unfortunately, when it is increased, tells us about news about the tumor. It grows very, very fast. Creatinine tells us about the image state, sometimes that information can be good or bad. of course, glutamine, glutamate tell us a little bit about energy metabolism. The MAA tells us about the health of our neurons. It should be the highest metabolite in the spectrum. And if it's terrible that you think that the lipids are really, really bad because they tell us about aggressiveness of tumors. So we have learned a lot from spectroscopy. And now that information we want to combine it with other elements. And actually, it's very, very powerful because if you look at the three important types of tumor in children, as we say, Tumours, adenomas, and glioblastoma, you can see that the profiles of the spectra are obviously different. So even some simple pattern matching allow us, if we compare them to normal brain, to be able to do diagnostic discrimination. Of course, not only that, we can look at the spectra, like in this case, we have a grade 2 astrocytoma. It's not such an aggressive part or an aggressive tumor, but it can become aggressive, especially if citrate as a metabolite is increased. So the increased citrate tells us that, unfortunately, this tumor might become more aggressive and the survivability be a problem. So through this kind of functional information and quantifiable information, we can have a better understanding of prognosis of the disease. And actually, in the in vivo and in vitro biochemistry, we have done on live patients, but also on tissue biopsies after the surgery, after we have treated with surgery. We have found that we can tell about good prognosis or diagnosis. These are typical Kaplan-Meier curves. I don't know if you are aware of them. There are neuro-oncologists use them all the time. So on the one axis you have probability of survival, on the other axis you have time. And usually if the curve is like that, like in the top, means that the survivability is good, while if it goes down, it means that the survivability is bad. And actually, as I said, because we have learned a lot about the properties of this due to biochemistry, when we measure in vivo lipids, increased lipids at particular points of the spectrum, together with inositol, we have seen that these children don't survive, while when glutamine and MAA are increased, the survivability of the children is better. So we are able to say more about, through the biochemistry and through the functional imaging approach, about the tumor's behavior. Now, I'm coming closer to the imaging side and the issue of texture. Now, if we look at diffusion, and apparent diffusion coefficients is a way to represent diffusion into maps of the brain, then we can understand more about the cellular representation of the tumor. So in this case, the astrocytoma has less cellularity. So this might be a good thing in the way we treat it. While the medulloblastoma has high dense cellularity. So the increased diffusion here maybe is a good sign. So that information, of course, we see visually. Later on, we can see how we can use it into machine-based algorithms, based on data analysis, in making some decisions. Furthermore, we can use functional anisotropy maps, part of tractography diffusion, to tell us a little bit about the structure and of the presence of the disease. And this is important for surgeons because, as you can see here, although the tumor is very obvious here with a lot of active disease and the black areas are necrotic areas, it's interesting that the nerve tracts are not affected. So the tumor can be dissected nicely by the surgeons and then followed up by chemotherapy. And that's another important information, visual information that we can use textually in our analysis. So, coming to this, let me do a quick crash course on architecture analysis. And apologies if I preach to the converted. But it is very difficult to do architecture analysis, especially in the field of MRI, because there are no universal definitions. The way we have worked the past 10 years has been very pragmatic, where we looked at the definition that comes from the original way we look at textures as humans, as radiologists in particular. So radiologists, what they like to do, and that's their job, they look at the spatial variation in pixel intensities in terms of anatomy, medicine, we can say what these mean. Okay? So based on these pixel intensities, though, they cannot do anything else but make a visual assessment. What we make the point is that with textual analysis we can quantify and we can capture patterns beyond human vision. So the idea we had was to work with radiologists and see how we can improve the diagnostic, prognostic possibilities in the work by textual analysis. Now the typical techniques we use for biomedical imaging, in particular in the area of tumors, are organized into three main areas. To textual feature extraction techniques that they are based on statistics, and I will explain a few examples of these. More complex mathematical approaches that are based on a wavelet transformation, and we use properties of wavelets to understand in different spaces what this might mean. And of course, we might use statistical models or model-based approaches like autoregressive models to be able to identify useful features. So let me give you the examples I have from my clinical work, just to discuss very quickly some examples of these. Probably, if you have done biomedical processing, if you have looked at the Gonzalez book, this is the most typical example we have learned at the university. So look at intensity values, and the histogram simply represents a count of these number of pixels with particular intensities, and we put it into the frequency space. And then we play with the statistics, and we use this as part of the discrimination. Now you will tell me what's so much about that. Well, put it into the context of the MRI image. That's my brain, apparently. This is what I was told by my students. After lunch, when I am at the hospital, I always feel tired and sleepy. And I always feel going in this country. I find the gradient noise very calming. And I fall asleep for 3 hours and then go on to the right in my brain. Apparently, they have seen changes, and I have a series of monitoring for the last 20 years. I've seen the changes as well. I pretend to not look at them, and neurologists don't talk to me about it. But it's interesting that if you look at the small variations into grey, white matter, the different regions show you distinct histogram difference. So we have more detail than the human vision can discern. That's very important. Now, the second order is more interesting because it looks at interesting patterns within an image. So, for example, we can look at patterns of pairs of pixels. So, in this case, we go to a particular direction in an example image space, and we count how many of these pixels might have the same value. And then we put them in a matrix, and then we analyze this matrix as a way of understanding these kind of statistics as a co-occurrence of particular intensities. So that's interesting because different kind of features that we can have can tell us a little bit more about the tumors. For example, when we look at this approach and particular features that look at the angular circumference measurement, then we can look at local homogeneity of the tumors. So these high values might say that this is an homogeneous tumor, which is good news. Because if we have topical necrotic areas, we have heterogeneity, this might be bad news. So contrast also tells us about local variation, again it can tell us about homogeneity, and then entropy can tell us about randomness. So all of these are very, very useful statistics. And actually there is a very several paper, it was written in 1973, so we haven't changed anything since then, but we have applied and improved them in terms of optimization. So Warwick has written a paper, it's an extremely good paper for students, and I always recommend it. It's a very old reference, I would say it's very good. It survived the citation kind of battle we have. Now if you go to high order, you can do exactly the same thing by but instead of doing it one time, you can do exactly the same measurements, the same approach as the co-occurrence matrix by running your measurements and looking at co-occurrences and pairs of these values into different directions of your example image. And then depending on how many runs you have on the direction of the vector, you might learn something more about the cause information of the tube. So now we have solved the ground morphosis, we can look at those textures, and of course this might tell us something about changes in liquidity, while long-run emphasis can tell us about smooth textures, which is very important when we look at the diffusion of tumors into the brain. While the first one can tell us about distinct tumors that are well delineated in the brain. So using all this, we try to do some of the work. I haven't covered everything, and this part was a little bit didactic, so I apologize again if you know about it. But again, there's a recently here, kind of recently in clinical radiology, where Castellano has described how we have used in CT and initial MRI experiments these techniques. And I would recommend it if you want to go into that area. So the challenges are to develop a pipeline that is almost semi-automatic and support radiologists to make better decisions in diagnosis, prognosis, and management of the disease. So first of all, we need to identify the modality of imaging we want to have, what kind of data sets, structural do you want to do images, diffusion images, and then we need to have a technique to remove the unnecessary information and focus on the information we're interested in. So segment is appropriately, and this is a big challenge in image processing, and there has been a vast amount of literature on how to segment and register this information appropriately. And we need to normalize it because, unfortunately, although we use the same protocol, MRI is so quickly into the condition that there are minor variations in the intensities you have on the original space. So we need to normalize it so that they are comparable. Then decide if you do two-dimensional, three-dimensional texture analysis, extract the appropriate features, and then use a technique to do a feature selection, then throw it into the classifier or do it in the workflow. So that's the idea behind that. So the first part of the pipeline is to find ways to segment these tumors. And depending on your technique, and depending on the tumor, you might be able to discern very nicely the tumor. Like in this case, I think this is again a parocytic astrocytoma. T2 image, you can see it very well, where it has the compartments, different techniques, different modalities show you different things. For example, the T1 post-contra show you that it has necrotic areas. So what we have done is we looked at the different segmentation techniques, but we came with an approach that combines a normalized multi-scale graph-based segmentation. So we use a graph theory approach to segment visually the tumors of the different images. Then we use the outline based on the segments to identify in the best possible way the outline of the tumor, and through an integration between that and the typical gradient of edge map. And combining this with a SNEC, we're able to come to an extremely good definition of these tumors. So radiologists want it, because they said, at least we don't have to do manual segmentation, we don't have to seed things, because you seed on SNEC like doing as the original MCAT segmentation approach. And that is a big challenge if we want to put this into clinic, because radiologists have about 30 seconds, exaggerate, have very little time per radiograph, so per image, so they have to look at that. Of course, normalizing them, the data is very important, and we don't do anything more clever than we have been doing in the past. Either a linear normalization, which is the simplest approach, but a little bit crude, or we try to look at local variations in big images in a way so that we do a piecewise linear normalization approach. And this allows us to do to put the images in the same intensity so that we can do first, second, and third order statistics when we have a model-based approach. Of course, the choice then is, do I do it on a slice, or do I do it on multiple slices? Or if I have a 3D volume, and somehow I can segment the 3D volume, can I do it like that? Of course, 3D volume segmentation is still very in its embryonic phase for clinical work. So what we are doing is we look at 2D representations. Again, a voxel there might have 18 indicators in all four directions, or 3D, which might give us a little bit more information about the neighborhood. And one of the things we have been studying most recently in the past years is that 3D capture is a better way to discriminate for diagnosis and prognosis. So I will give you some examples of how some of our work has happened and what we have achieved until now in the 2D space and the 3D space. So as you see, again, most of our experiments don't include hundreds of children. That's fortunate. We have a whole UK database, which includes, for the past 15 years, 750 cases, which is again fortunate. I work with adults, we have thousands of cases. So that's a positive thing. But as I said, the challenge is we cannot resect, we cannot biopsy. So we need to do everything non-invasively. So, in our first experiment, one of my PhD students, who's now in Cyprus, has looked at the three major categories of tumors, and we looked at T1 and T2 structural MRI. We did manual segmentation originally, and then we used the various typical TA texture analysis statistics. And again, through supervised learning, we reduced the features with principal component analysis. Then we used the neural network and linear discriminative analysis classifier, and we validated all this. We have to validate everything because we have 40 children. So we do the link one out analysis, we track anything, on the color techniques if we want it. And what is interesting, when you compare the results with radiology and the gold standard of histopathology after the surgery, 90% accuracy was the result of infection analysis with probabilistic neural network without us putting any information on the classifiers. Although the LPA at the time was a little bit poorer. Of course, we learned more, and most recently, we looked again at the same cohort, and we added diffusion, an extra dimension, and we looked at normalization, something we didn't do initially very well with the crude approach, so we did the piecewise and the Y approach. Although we did manual segmentation, and then we looked at particular histogram statistics, and the results were a little bit more impressive if you use classifiers which are more flexible, like machine classifiers. And 79% classification accuracy for tumor type was excellent, and up to 91% using diffusion rate images. Radiologists were ecstatic. They were saying they are destroying our job. On the other hand, it helped us a lot. So recently we moved to 3D, increased our children cohort, because this is the last couple of years. Although we started with 12 last year, it was 2 years before that. And again, we looked at structural imaging. We looked at more features and a series of supervised learning classifiers, and we achieved an improved performance with 3D trained SVM as part of the classification. 90% accuracy improvement from 2-dimensional data sets. And again, this was verified by the biopsy-based pathology, which is our gold standard. And finally, what we have decided, okay, we need to increase our numbers properly, so we Children's Hospital Board, University of Birmingham, UCL, Renton Street, and Nottingham University and the hospital have looked at expanding the study and see the efficacy in 3D. Now, what is interesting is that because of different conditions, we had a variation between 60% and 86%. And actually, the optimal features depended very much on the way we were putting the approach for the normalization and which was our main features as part of the presented data. So still though, 86% is very, very positive. And both the hour was renowned for her visual acuity and also her work in this area. She was saying, I'm impressed. And she said, I'm impressed, I'm happy as well. It's like every time I talk to her, I have a vibe of my. Now, finally, I have an example where I show you what we have done with prognosis. So what we did a blind experiment now. We looked at three-dimensional texture analysis features, but instead of looking at specific diagnostic elements, we looked at children that survived beyond 40 years and children that didn't survive beyond 40 years. And actually, as this fishing exercise, we found that 15 textual features are significant to tell us about survivability. This was shown in particular features of T1 and T2 imaging features. So immediately, then texture analysis can tell us about survivability, can tell us about prognosis, so we can plan better the treatments. So, an interesting approach. We can characterize tumors, we can diagnose them, we can tell something about prognosis, we can learn about how people respond to treatment. However, there are some interesting unanswered questions. And here is the challenge, mainly from an engineer, but also from clinical biological engineering. A lot of this data is collected in different protocols, but because of lack of time and because children are very sick, we tend to not have all the data sets. So we have a missing data problem. And that's a very interesting challenge. If anybody wants to do a PhD on this, or 2 PhDs on this, I'm very happy to supervise them. So we are very interested to look at that, but also our classics might be imbalanced. The ones are very, very rare tumors. So we don't have the same kind of weight, and that's a challenge. It's not simple to do weighted textual analysis because again we have low numbers, so our cross-validation is completely destroyed. So there are interesting challenges that we have to look from the point of view of data. Of course, from engineering, although we know a lot on segmentation, how do we do the most optimal segmentation for that? Which is the best part? The solid part, the necrotic part, the cystic part? How can we segment in 3D? We have amazing 3D visualization with MR imaging. And what is the most optimal feature selection? So these are a lot of open problems that you have to find these features. And of course, we need to understand what these features mean biologically. We started with spectroscopy, and we are moving to putting all modalities together. And just to close that, show you an important example. If you use the structural image of this particular neuroblastoma case, we see a tumor that is all over the place, and there is an area away from the original tumor that we think, oh, this might be progression, or the child has metastasis. And we look at the spectroscopy in this area, and actually we see that it is not progression towards healing, it's progression towards disease. If we combine it with diffusion and diffusion, we can see that we have a tumor relapse. Now, we have done this visually. We started doing this experiment with texture analysis, and our accuracy has improved quite a lot. Again, in that range, up to 80%. So it is very, very important in these cases where radiologists and oncologists have to make a decision. To go back to more aggressive chemotherapy, radiotherapy, or is this something that I should worry? It's just pseudo progression, or in the case of bad news, or it is something that says that everything's okay. So that's very, very important. And finally, when we fuse data, it's essential we use texture analysis to quantify better. This is the example of one that has been there since I was doing my PhD, but we perfected it very recently with compressed sensing techniques from an engineering point of view. Where we combine the structural images with spectroscopy. And in this case, we have a terrible astrocytoma that takes half of, well, quarter of the brain. And it has two compartments. Radiologists couldn't make a sense of which one was the most aggressive, it could go into biopsy the essential parts of the brain. So by combining this microscopic imaging, using textures and other features, we were able to build these maps that tell us that this part is less aggressive, it's a low rate, and this part is more aggressive. So surgeons went to move that part, and for the rest we just radiotherapy. Letting their own boy survived for the past 5 years, and now he's out of our care and going to Yarmouth Hospital. So it's an amazing story. So I close my talk by saying that we have some good evidence that these techniques are very important in cancer diagnosis and provide non-invasive biomarkers for diagnosis and treatment. And I think engineering and image processing and biomedical engineering can make a difference. Of course, we need to, as engineers, optimize the manner how these results can be verified so that later on we can incorporate them into clinic, so that we can have a quick translation of an engineering operation into clinical care. And of course, we need to do that with many trials across different centers. Just to say that all these work has been there for the last 15 years, spectrum analysis for the last 5 to 6 years, and we're very grateful to our funders to acknowledge them. And you can see that this is not a small group of people. So one PIs, based on the status, and great research group, especially Ahmed and Sushata, have been my experts in spectrum analysis. So thank you very much.
Thank you very much for this excellent presentation. Thank you for reminding us what is behind the picture, behind the images we see. Now the talk is, the presentation is open for discussion. Yes, Mr. Arvanitis.
Thank you very much, Professor Arvanitis, for the inspiring presentation. And I'd like to comment on the aspects of texture versus all other biological issues. With texture, I think we can get as much information as we can on the structural position of the tumor, but it seems that from biology there are other aspects that control and characterize different submodalities or subclasses of the same tumor. And I think the importance of such other information is, in addition to the texture, as you mentioned, very important in order to characterize the subclasses of tumors. I'd like to ask for your experience on these aspects of multimodalities.
Yes, so I haven't discussed at all what we do with quantification from the imaging side, plus any other information that comes from the genomic, proteomic, and metabolic level, which we do at the level of the lab. So from the imaging side, as we have seen, we have so many modalities. So fusion can tell us more about particular specific characteristics, with quantities from metabolites and also quantities from the imaging characteristics like particular mass, phase mass, tittle star measurements, relaxation measurements. If we fuse these, we can start stratifying on subclasses of the tumors. In particular, recently, and we hope the paper will get accepted and some we have managed to show that what the biologists have been claiming for some time, that metabolostomas in children are not a single type. We have 4 genetic types. And actually, we have managed to stratify them by combining some texture information, some diffusion information, and some quantification from in vivo spectroscopy, and corroborated the evidence with genomic, microarray data, and some NMR metabolomics or tissues we took out. We did the same spectroscopy, but on high field NMR, where we verified our findings. So we're going towards that direction, and we're absolutely right. This is the way where we have managed to create what the Americans call personalized medicine, and in UK we like to use the word stratifying medicine. And it's very important for the clinicians. The clinicians can make better decisions on the basis of that. So, indeed, this is just only the part of the story. An image is 1,000 words. I think this is part of the 1,000 words, and there are more words to use as part of our experience. And that's why I think as biomedical engineers we need to work with interdisciplinary teams. In my team I have clinicians, engineers, computer scientists, I have 3 psychologists, I have 2 geneticists, and I have a biosensus person. So it's part of that kind of work.
Thank you very much. We can take one more question because of the time. If I will take this chance to ask a question. You said about prognosis, and you identify some issues that some of them are metabolites. Do you think that we can influence those metabolites for treatment?
That's the ultimate kind of holy grail from the point of view of biologists. Although oncologists want to do it in a direct way, they want to do it through radiotherapy and chemotherapy. But targeted new agents, new drugs, biologists want to understand better how the information from the metabolism correlates to other relationships in the genome or particular aspects of the subsets of the genome, and how these relate to enzyme reactions in protein, folding program. So I think this is something that is very, very important and will shape the creation of new drugs. Although at the moment we are battling with aggressive chemotherapy or targeted chemotherapy. But the first stage we need to understand we have been using these platinum-based drugs. What do they do? By simply observing the metabolites. And later on, I think, as you said, we'll be very, very targeted, and hopefully working with the bioscientists.
Thank you very much. Dr. Arvanitis, I would like to thank you again very much for your presentation, for accepting this invitation to be with us today, and congratulations for your work, and wish you the best for the future. Thank you again very much.